Good afternoon, everybody. Welcome all to the afternoon session of third day of Platinum Jubilee celebrations here at RRI. So we have 3 speakers today, and after 2 talks, there will be a tea break, and then the third talk is in an online mode. So we have different topics in today's session. It starts from quantum computation to quantum gravity and goes to condensed matter theory. And the first speaker of today's session is Professor Urbasi Sinha. She is a faculty at LAM Group, and she works on experimental quantum computation. And today she is going to talk about photonic quantum science and technologies. I welcome her. Thank you.
Thanks. Can you hear me at the back? Yeah. So thanks, Vishnu, right?
Yeah.
Thanks a lot, and apologies in advance for overrunning. Yeah. So even before I begin the talk. So of course I want to thank the Platinum Jubilee Committee. We have some members here for actually thinking of this very nice idea. Otherwise we never seem to talk to each other than at corridors, right? So it's very nice that we actually have a forum where we can tell you a little bit about what we have been up to. And in my case, it's a little more than 10 years what we have been up to. So this is a great idea, of course, and it's gone so well so far. So what I'm going to talk about is, of course, what we do in the lab, which is photonic quantum science and technologies. I belong to the light and matter physics group. And many of the talks that you will hear and have heard have been on the matter aspect a little bit. So in some sense, I feel this is a very fitting cartoon. In some sense, photons don't have mass, so they don't really matter, right? I mean, that may be the thought that you have, all this cold stuff, So we are very warm people. We are not cooling anything, and everything is at room temperature. So that is what differentiates us, let's say, from all the cold colleagues that I have, right? And of course, this appeared in a different avatar, but I'm going to spend the next 40 minutes in telling you why photons actually do matter, even if they don't have any mass, right? So that is the basic overview of what I'm going to do. And this is how our journey began. And, this is a group of people who very kindly came down for our little lab inauguration that we had. This was December 2012, precisely 9 months after I joined RRI. So we had to have the lab open the same year as I joined. This was one of those, when I was a young person, I had these sort of fanciful ideas. So, but it did work out, right? And so we did open. And so here we have Barry Sanders, who's also here, has been coming to RRI for several years since, right? And so these are the 3 people who kind of formally cut the 3 ribbons, Ray Laflamme, Gregor Weiss, and Thomas Zenewein. And that is also very symbolic because, an experiment that we have all done together is a triple slit experiment. So this was again another bright idea to have 3 ribbons instead of 1. So it started off on that note, and so here we are doing what we do. A lot of what we do is actually much motivated by this, this little line here. Although let's not go into the context of this line, that's not what we do. But having said that, we are working in some sort of a semblance, between working on fundamental science ideas and then applying them to applied technology. So we are working on both domains, not just on one or the other. And so in some sense, we truly believe that today if we are working on something which we can't claim has this big application for the grant proposal, it will come up in few years' time if we do a good enough job. So, we are trying to maintain this healthy balance between science and technology. And of course, this field has become more important as we go along. And there is this national mission which is coming up, which is going to, sort of have a lot more research happening in India in quantum science and technologies is the hope. So what is the big picture? And I don't know cosmology, I'm not an expert in these topics, so that's not the question to ask. But we do know that our understanding of things around us is rather incomplete, right? And so, there are experts in the audience who work on these ideas. But then for us, we do believe that understanding what we understand up to a very high level of precision is very important. So for us, it's quantum mechanics, right? So principles of quantum mechanics that we are used to, we want to put them to stringent tests and try and see what kind of bounds we can set for these various principles. So that has been something that I have been working on even before coming to RRI, and we continue to do that in different precision experiments that we work on towards these various principles of quantum mechanics. So that's one of our main areas. The two applications that we are focusing on are quantum computation and quantum communication. So quantum computation, of course, we had a lovely colloquium last week by Barry, where he talked about the big picture, where the field stands and so on. But having said that, we are working in a slightly different domain in computing, as we will come to a few slides down the line. And communication, of course, is something that sort of demands photons. There is nothing better than photons to communicate with. Photons, they don't have charge, they don't have mass. They can go a long way in taking this information, and in some sense have the ideal characteristic to communicate. So we are, of course, using photons to work on all these ideas. We have a class 10,000 clean room. That brings me to an anecdote. So when we started, this class 10,000 clean rooms were not popular at RRI. So I had to write a 100-page document with, Mr. G.B. Suresh, who I have to thank here for helping me with writing a document to convince Krishna, who was our administrative officer at that time, that we needed this, needed this modulation of temperature, humidity, and so on for our experiments. And so now we have more come up after that, and so that has been very pleasing. So this is the kind of environment we created in the telescope building, because we actually got 2 rooms which were go-downs. And so when we built our lab, even the roof had to change, because along with it went a telescope. And so even the roof had to change. So it was a journey, I would say, taking it to a room, to a clean room and beyond. So this is, a snapshot. So these are the various areas, as I mentioned, we are working on. And of course, I will, just in case I run out of time, the idea is to acknowledge the various people in the beginning itself. And so these are the various people, mostly smiling faces, who are currently members of the lab. And that is, of course, the reason why we exist, right? So without that, just staring at a laser anyway is not a good idea, and it won't help. So, this is the reason why we are where we are. So these are the current members, and these are the former members who are also, doing very nice things as they have moved on. And so I am eternally grateful to all these people for what they have done. And of course, there are other kinds of people who are, of course, collaborators. We can't just be in a little shell and do things without talking to others. That helps in improving our science. So we have a large list of collaborators both outside the country and within. Special mention again, Barry Sanders, who is a Vajra faculty at RRI, sitting in the audience as well. That's very nice. And so we have done a lot of interesting work together as well. And so these are the list of collaborators in India. One person I would mention is Som, who actually helped us learn about microwaves and do an experiment on an open field, which gave us a little bit of confidence even to go on to these satellite projects and so on that we are doing now. So we have, an eclectic group of theorists and radio astronomers in our collaborator list. So this is the snapshot. Go to the website, because very little that one will be able to convey in the 40-minute time slot. So it's always there for you. So going to a little bit, especially because I do see a lot of students who are not from the LAMP group, just a little idea as to why most of us do what we do. It probably is motivated by this, very famous quote attributed to Feynman, where he says, he can safely say that nobody understands quantum mechanics. But this was 1965, and if we still claim that that is true, then we are not really that smart. So I would say that, we understand a bit more than what perhaps he did, but there's a lot more to understand, and that is what keeps this field very exciting, because it's this, so-called quote-unquote mystery which makes all these applications possible. And so we are still understanding many things. But having said that, the impact of quantum in daily life is something we may be taking for granted. If you're in an MRI machine or you're using this for laser eye surgery, these are all examples which are using quantum mechanics already. So, the use of quantum mechanics in technology is not new. It has been around for a long, long time. And so what we are now focusing on are other applications which are gaining prominence as we speak: computing, communication, sensing, and so on and so forth. So this is, just a reminder. And of course, another reminder that this is a field which has a very rich history and legacies, with all these very, very, seminal contributions from various people. And funnily enough, all of them have been awarded the Nobel Prize in Physics for all these contributions. So it is one of those fields which has a very rich, number of people who have been given the Nobel Prize in Physics for their contributions. So these are all such people. And these are all people I'm sure we recognize from our textbooks, and also if we are working in this field, we should just be able to name them I don't want to ask Soumya this question, but you should know who these people are just like that, right? So this is what it is, and this is where we are now, where we have this sort of claims, from these companies making bigger and bigger machines towards your quantum computer, and all this is enabled by superposition principle. So this is where it is, these are the fundamental principles which enable all these ideas that we work on. These are the various list of devices, okay? And so we of course have photons, but we have ions, we have superconducting qubits. We have many such approaches towards making this quantum computer, and there is no winner yet, and that is nice because we can continue doing what we do. Something has an advantage over something else in some property, but then we don't yet have one architecture which is what we would go ahead with, right? So there's a lot left to do here, and these are again two gentlemen, Sergei Haroche and David Wineland, who won the Nobel Prize in Physics in 2012 for manipulating single atoms and photons, right? So this is where it is right now. Having said that, I go to photons because, as I mentioned, that is what we do, and the students who are usually at the back, if you are interested in knowing more about these photons, do read this review article which kind of tells you how to make photons. So you might think that photons are straightforward, we have light everywhere, so what is the big deal? Why should a lab exist to make photons? But of course, that is not true. So when we actually go down to the single photon level, it's not just about dimming down some light and getting it down there. You have to have specialized ways of doing this so that they satisfy the right statistics, right? And so then, having said that, there are many ways to do this. The ones we work on, I will just show you. So these are our current areas of research: photonic quantum information processing, studies of entanglement, computing, communications, fundamental tests, as I mentioned, and quantum optics. So this is the general overall framework that we work on. So here we have a video which was working 10 minutes ago. And so this sort of tells you how we make photons in the lab. I don't know if it is, the room is dark enough for you to see, but then the video is playing right now. So you can, I think it is quite okay. So here you have a nonlinear crystal. What we do is we shine a very strong laser on this nonlinear crystal. It happens to be blue in color for this purpose. We also work with blue laser a lot, 405 nanometer laser, right? And so this gives rise, 1 in 10 to the 8 or 10 to the 10 of these pumped photons gives rise to a pair of photons, okay? And so this pair of photons comes out in the form of a cone by solving the Selmyer equations, and the cross section of a cone is a circle, and this is what you see, and that intersection point there is what defines the entangled state. Because that intersection point, just if I just pause for a moment, the intersection point is important because you do not know a priori which cone it belongs to. If one of the photons belongs to the right, the other is left, and vice versa. But because you do not know a priori, that is what defines your HV minus VH state, for instance, which is a Bell state. So that is how we are harnessing entanglement, and this is a picture from the lab. So, different types of photon sources which exist, we have 7 or 8 of them, and so some of them are entangled. And so this is, just in lieu of a lab visit, so to speak. If you walk down, you can also visit the lab. This is all RRI people, but this is how the blue laser is being guided through different optics. I won't get into the details of all the optical components, but it's being, it's sort of being focused on this nonlinear crystal, which you can see. So this is the crystal, okay? And so this crystal, at this crystal, you harness what is called the Chi2 nonlinearity. Reggie mentioned quite a bit about the various, Chi2, Chi3 processes and so on. And so Chi2 nonlinearity is what we use, and we have this pair of photons. But then once we have this pair of photons, how do you know you have it? Because these are single photons, you don't quite see them. So you have to do some dedicated measurements to prove that you have these photons in the lab. For that, what we do is we make use of what is called a coincidence measurement, okay? And so what is a coincidence measurement? It is as it sounds. So these two photons, they have come out together. And so if I measure one of them in one detector, the other one in the other detector, and if I measure a correlation between these two detectors, then that leads to the formation of a peak because they are coincident. Yeah. This is actually a coincidence peak from the lab. Yeah.
Other peaks are very, two circles and then they are
yeah.
considered. So you're saying that the photons are the points where they are this thing, but what are you seeing, that other thing?
Yeah, so they are all photons. So essentially the idea is that, if you
so these are like two light beam I am seeing.
We are seeing them on a highly intensified camera, that's why we are seing them.
Yeah.
So if one of the photons is, in the left circle, let's say here, the other photon will be phase matched and it will be on the perfect, right circle. So you have pairs. So we see all of them in one shot.
So these are like over time.
Yeah, it's over time.
Over
So
time.
we have a camera. So we have millions of photons which are impinging on it.
Yeah.
So it's a 1 second window, let's say.
Yeah.
In 1 second, we have the whole cone light up. So at a time, of course, only one pair will come out. But in 1 second, there are
So
millions
then,
of them. Yeah.
from that picture, like you are saying that the 2 points, how do I know that these 2 points are correlated? Something
That is what I was just showing you.
Yeah.
So, you won't know, right? That is, of course, the point. So, you won't really know what is correlated. So, if you are going to actually have your, fiber, so we are going to couple these photons to a fiber. So, your fibers are going to couple from 2 different points of 2 different cones. And so, that is where the alignment is. So, this coincidence peak that I showed you doesn't come in a day. So, we have to actually keep on changing the position to ensure that we are dealing with a pair of photons which belong to the same mother photon. So, not all the photons are pairs, right? So, what we would usually have is nothing. So, we would end up with 2 positions which are not correlated.
Yeah,
then we would have to do precise alignment to get this to work. Yeah. So, that is why this coincidence measurement is important. And, once you get a little peak, then it's easier to align further to get the peak to shoot up. Otherwise, the first part is, of course, you lose some hair because, you don't really know exactly where to put it. And that is where, of course, the alignment
and this
becomes very
coincidence
important.
measurement, basically you are just telling you they are arriving within some delta t time.
Within a small delta t, which is the width of the peak. And so that is in a nanosecond or something like that. And that happens, your detectors also have electronic noise that causes a jitter. So anyway, you can never be 0. So picosecond, nanosecond is the kind of, was that clear, Sanjeev? Yeah, I'll move on to, because.
How much spatial precision you need for getting good coincidence?
So we are, coupling to a single mode fiber. So it's a 5 micron core diameter. So it's very, very precise, right? Okay. So we are using MBT stages from Thor Labs and so on. Yeah. So, okay. So going on to that. So this is again, a snapshot of these. So when we took the pictures several years ago, we were very excited by them. And of course, new students will also be excited when they take the same pictures. But then so from now on for the next, part of my talk, I actually will be, showing you little pictures of the students who have actually made these things happen, especially the ones who are currently not members of RRI anymore. So, I just want to acknowledge them going forward. Devadrita was the first student in my lab, really, and has built this source, the first one that you just saw, and she's currently a PhD student in Groningen. So the first part, as I said, it's the major part where I'm going to focus on fundamental quantum optics, precision tests of quantum mechanics principles, entanglement and quantum information. So I'll tell you a little bit about the work we have done in this domain. That brings us, of course, to the Nobel Prize in Physics 2022, which was given to Alan Aspect, John Clauser and Anton Zeilinger for experiments with entangled photons, establishing the violation of Bell inequalities and pioneering quantum information science. We have been hoping that they would get this Nobel Prize for a while. It's much delayed in the minds of the community, so it has been extremely pleasing. But of course, for the group of people here who are my lab members and me, it is even more pleasing because this is what we are doing in the lab. So it's because of these people that we can now think of new ideas. So they have pioneered the field and we are working on new ideas in this. So there cannot be anything much better than that because we are working with photons and entanglement. So this has been particularly, we've been very happy. I think we also cut a cake. And so having said that, focusing on Anton Zeilinger, this is the timeline of the Bell inequality, okay? So from the back, maybe you are not able to see it very well. It's 1935, we have the EPR paper. In 1964, we have John Bell who comes up with the, inequality. And then several experiments have happened which have violated Bell inequality. I won't get into the details. Perhaps I'll give a talk later on this month, just focusing on this as a part of this Vijnana Kathikelu series. But then what I want to, however, say today is that Anton Zeilinger's contribution to this is, in fact, he and his colleagues, they demonstrated what is called a loophole-free violation of the Bell inequality. So a loophole-free violation took, let's say, more than 50 years to reach for the Bell inequality. And so this is what makes this a Nobel Prize winning contribution. This was his part in the Bell inequality violation and his colleagues, of course. So these are the 3 loophole-free Bell tests which happened in 2015. And so this is one of them. This is the one from the Zeilinger group, okay? And then there was another one. And so why is a loophole-free test so important? Because, Bell inequality violation, we say that it proves violation of local realism. We are not getting into Bell. But then having said that, there could be other alternative explanations which come through because of inadequacies in your experiment, which people would claim that, this may be the reason why you're having the violation, or your detector is not 100% efficient. So, this is what makes this not complete as a demonstration. It's only when you close these known loopholes that you sort of reach a stage where, it can be used for the applications which we are all working on, whether it's quantum key distribution, random number generation, so on and so forth. Till then, there is this question mark. Is there some other way in which I can explain this? So loophole-free test makes this, contribution. And of course, again, a very pleasing thing for us is that this year itself, we have done a loophole-free violation of another set of inequalities, which is called the Leggett-Garg inequalities. Again, has a rich history of experiments, but then with loopholes. So we are the first people to work on and demonstrate loophole-free violation of the Leggett-Garg inequalities. So it's very, very pleasing to us that it's the same year that a loophole-free test has been recognized by such an important forum. So this is the experiment I want to tell you about for the next couple of minutes. And this is a topic that I talked about in the in-house. So maybe some of you have already heard about this. This is, of course, a violation of what is called macro realism. Okay. So what is realism? Now, realism is that the classical realist worldview, it states that a system is in a definite state in which all its observable properties have definite values independent of measurement. Example I would like to take is my student Soumya. He is looking at this slide with a lot of attention. If I look at the slide, he continues looking at it with a lot of attention, which means his act of looking is not dependent on my looking at him, at least in this talk. So this is what I'm used to, that tree remains there even if I'm not looking at it. This is my classical realist worldview. Unlike a classical state, the specification of a quantum state does not in general give the values of the dynamical variables possessed by a system. Thus, in general, a dynamical variable is taken to have no definite measurement independent value. So you could be looking at the screen, you could be jumping, you could be dancing, whatever it is, you do that well. So all this you could be doing, and only when I'm looking at you, you collapse to one of these things. That is what a quantum state does. It does not have a definite, property independent of measurement. This is the fundamental difference. So a measurement according to quantum mechanics in general does not reveal a pre-existent value of a dynamical variable. And so this puzzled Einstein. He's quoted to have said that he likes to think the moon is there even if I'm not looking at it. Okay. And so then there are these two different, notions that people have followed through over the last several decades. This is the one which is very much popular right now, which is about local realist inequalities, which involve bipartite or multipartite systems. You do Bell inequality violation, and if you do that, then you are able to violate local realism. What happens if you have a single particle? Suppose I don't have an entangled pair of particles. If I have a single particle, what is my comment on its realism? So then, of course, you need to make use of the other property, which is superposition. And so by making use of superposition, you can have a macroscopic superposition of two or more, definite states, which is what is used by Leggett and Garg to come up with the Leggett-Garg inequality. So the Leggett-Garg inequality is a temporal equivalent of the Bell inequality. In Bell inequality, you have these systems which are not co-located, and you are violating Bell inequality, etc. But then if you have a single system which is evolving in time, by measuring correlations between its state at different instances of time, you have a temporal equivalent to the Bell, and that is what is the Leggett-Garg inequality. Equally important, of course, because otherwise you won't have anything to say about systems which are not entangled. So that is where Leggett-Garg inequality comes in. And, the original motivation was to keep on increasing the size of the system to see how far you can go before, quantum mechanics stops being applicable and so on. And there are several experiments, of course, which have been done in Leggett-Garg inequality. Having said that, what makes our experiment special is that it is the first loophole-free violation of the Leggett-Garg inequality. So that is, of course, we just established why a loophole-free violation is important. And we have done this in a very comprehensive way. It's a talk by itself. So, if you have a lot of questions, we can do it after, or, short questions now, because I do want to talk about many things, brimming with enthusiasm. But then, this experiment is something which has so many sub-experiments where we have actually analyzed all the non-idealities and come up with the expectation from quantum mechanics. And our experiment matches quantum mechanics perfectly, which is also very important as violating macro-realism. Yes, I knew, yes, go on.
No,
Yeah.
like when you do this two-time
Yeah.
measurement, so here also you have an entangled system.
No,
It's a single system.
Single system.
So I can have a particle in a box, for example.
You can.
And I make a measurement.
So-
I find a position. I do a position measurement.
No, I do a measurement, so depends, you see, what is it that you're measuring? I will do measurements in different instances of time.
Yeah.
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 I won't talk about position in this case, just to.
No, but just to make it simple, I don't like. So suppose I have a particle in a box.
Yeah.
Just this thing, and it's a single system, and I make a, let's say, position measurement at one time, and again I make a position measurement after some time.
So there is one correction to this.
Yeah.
You can do this.
Yeah.
Having said that, this particle in a box needs to have a macroscopic superposition between two different states, whatever that is. Now, in your case, you know,
It can be two energy states.
Yeah, it could be two. I mean, I don't know how I would go about, making it macroscopically distinct. That is a different discussion. What we have done, we have taken a single particle which is either following the upper or lower path of an interferometer.
Okay.
So those are two macroscopically distinct states, upper and lower path, and then I have a concatenation of interferometers, that is a detail. But having said that, what I'm doing is at a given instant of time, I'm figuring out whether this guy is in the upper path or lower path. This is my dichotomic observable. Okay, and so this
then can I just think of it like a two-level system? And
two-level system
I
where
have a
you can
two-level
have
system. I make a
access-
measurement. I'll find the energy level again after some time. I make a measurement.
Yeah.
So then, what is the quantity
Yes,
observable?
so
I'm
the quantity that
constructing?
I'm measuring is a correlation function, okay?
Okay.
So I'm actually doing some, so for instance, again, I'll give you an example which we have obviously done. So we have this photon, it is going through two concatenated Mach-Zehnder interferometers. So in the first Mach-Zehnder, it is in the lower path or upper path. Then what I'm doing is, I actually go on to the second one, again the possibility lower and upper. So there are four possibilities which emerge, upper, 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 lower, lower, upper, lower, lower. So when I'm detecting, and of course, that is where the coincidence measurement comes in and so on, a detail. But then when I'm detecting, I will be able to know whether I'm doing plus, 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 minus, minus, plus, or minus, minus. So these are the probabilities that I'm detecting. Of course, I'm doing many detections so that I can measure probabilities. It can't be a single measurement. So ensemble of measurements, and I'm measuring the probability of P plus plus, P plus minus, P plus minus plus, minus minus, and it's actually 3 times. So it's plus plus plus, plus plus minus. So there are 8 which
And
go
it's
into this.
supposed
That's the
to
detail.
satisfy some inequality.
That is going to satisfy some inequality. Just like in the Bell case, you have 4 such joint probabilities, plus plus and minus, we won't discuss Bell for now, but then in the Bell case, you have 4 such joint probabilities. In the Leggett-Garg, you actually, in this case, the 3 times we have 8. And so it's a similar idea, but in time. You got it right. And of course, as I mentioned, now we use it for all these applications. So this is the thing I wanted to just show you. This is the experimental value. This is the quantum mechanical range, including the non-idealities. You can see they match very well. Yes. Yes. Yeah. In fact, I can show you we have mapped it also in terms of unitaries, which I can show you offline. Yeah. Yes.
Yeah, so these are all these particles, like these are in superposition states, right? So now, like you mentioned, for a statistics, you need to mention over many such like many particles to get a get probability distribution.
Right.
So, do you need to confirm that actually that they are like before your measurement actually in a superposition? Because I'm worried about like if some error is introduced, like
Yes.
do you have any handle?
Yes. So, and that's a very good question, because you see at the end of the concatenated Mach-Zehnder, in our case it's Sagnac, but a detail. So 2 interferometers, let's say. So the end we are actually measuring an interference. So we of course are increasing the visibility so that the constructive and destructive of the visibility is actually for us it's almost 90%. So we know that indeed without superposition you won't have interference. It's only when the particle is going through, I don't want to say both paths at the same time, but when it has equal probability of up and down, that is when you see the interference. If you block one of them, then you don't see anything in one of the detectors. And we have done several of these blocking experiments to actually give us the baseline as to what is our,
Oh, I see.
error.
So your probability measurement is beyond the,
Oh
those,
yeah, much beyond. So it's in So that's why I said so many sub-experiments to rule out, and this is a great question, and there are many other such questions.
Okay.
Yeah.
Thanks.
You have a question, Arunda? No. Yes, Shonjukta, yeah.
In the first two rows of the second table, so you have the value 0 in spite of taking the experimental non-idealities. So why is it so?
Yeah, and that's also a good question. So what is happening is that, these two are coming from the first, so as I said, there are two interferometers, right? So the first one we are using to mark the paths. So the photon is up or down. There is no interference in the first part. After the second beam splitter, the interferometer which comes in has the interference. So now these two guys, T1, T2, T1, T3, they both involve T1. Okay, so again, algebra I don't want to get into, but because of that, the interference term does not come in here at all. So it's kind of perfect. It's only when the interference comes in that the visibility not being 100% plays a role, which I just said is close to 90 for us. And that is why, we have this, only the T2, T3 captures that. But here, there is no non-ideality, so to speak, because the number is expected to be 0 and nothing is contributing to making it non-zero. So it is as theory should be, but then this one not so much, yeah? Is that good, Sanjukta? Yeah. Okay, so this is of course us with Tony Leggett when he visited us and we celebrated his birthday, and this is Kaushik who contributed as a PhD student to this experiment, major part of his thesis really. Okay, so, and we got some attention. New scientists told us that we are the most watertight experiment of all time, so made us feel proud for all time. Going on with the same genre of precision tests, this is an experiment which is on the Hongo-Mandel interference, and I'm very glad that Barry is giving a talk on Friday. He's going to cover this experiment as a part of his talk because he has collaborated with us on this, so I'll skip details on this experiment. It's a beautiful experiment, but you can ask Barry the questions. Then we have another one which is on a new quantum state estimation problem. So of course, we think about computing, communication, all this is fine, but what about the knowledge of the state? How well do we know what is the quantum state we began with? So quantum state estimation is a very important problem, and usually what we do is what is called quantum state tomography. So it's like the CT scan, the T is the tomography. So you have your brain, and even my brain, which may not be that great, I don't want to destroy it. So what will I do? I'll have different slices, different projections which we'll have pictures of, stitch it together, and I have a picture of the brain. That is what we do with a quantum state. We don't want to destroy it either. But that has a problem. The problem is that as you go higher in dimension, D, let's say, the quantum state tomography requires D square number of measurements. So it shoots up very, very quickly and becomes rather intractable. And so we came up with a new way of estimating the quantum state which actually avoids tomography. We call it quantum state interferography, where we are answering this central question that if I have can I have a device with which without any change of internal settings, I can determine the quantum state of the system just by measuring an interference pattern, which we do rather well, okay? And so this is an interferometric method to estimate the quantum state. This is the schematic from the lab. And so we also show how our method scales with dimension. That was the point, right? So for 2D, it is one single shot measurement. But as you go up in dimension, it is D minus 1. So the scaling is linear as opposed to D square minus 1. And so, of course, there's a lot of detail here. Having said that, we hear that there are quite a few groups who are working with higher dimensional systems and using QSI. We have shown this for qubits, and it has worked very well, the theory and experiment. Yeah. Increased number of levels for the quantum system, so 3D, 4D, which we will come to anyway, and we got some appreciation. So this is another set of experiments, and so these are the 3 students who contributed. That's why I highlighted them. This is on testing superposition principle, Born rule, and higher order interference in quantum mechanics. So I bring you back to the first page of Quantum Mechanics 101, which is the double slit experiment. Okay, so I have a source here, I have a detector here, and it's a source of some waves. It's always, it could be electromagnetic waves, it could be some, but that's a wave equation that we are solving. So if I open only slit A and close B, I want to call the solution psi A. Okay, I keep A closed, B open, I call it psi B. Question is, when I have both of them open, is the solution psi A plus psi B? And of course, that is what is used in various, we have also been using exactly this as a solution so far, okay. But that is of course not quite true, because these are different boundary conditions. So when you open a single slit, it is a certain boundary condition. Second one is a different one. Third one, when you open both, it's different, and beautifully captured in this work by Yabuki et al., where he showed how you can use Feynman path integral formalism to actually come up with these paths which cross the slit plane more than once, which will only come when two slits are open. If you open them individually, you'll only have them go individually. Only when you have both open, these possibilities emerge. And so he showed this. Yeah. Yeah, this one.
The psi plus IV, one way to think about it, which may be not experimentally very useful, but is to say that the set of paths which go through A first, and the set of paths that go through B first,
Yeah.
even without closing or doing any of that,
Yeah.
this is a very good way to partition the
Yeah.
paths. And
Yeah.
I don't know how experimentally viable it is,
Yeah.
but that's one way of, at least theoretically thinking about psi plus psi.
I agree. That is a very clean way of thinking, but I also agree with the second part of your statement that, it's very difficult to figure this out. And so that is why this paper had a little bit of an issue, because they also talked about point slits and Planck length as a requirement. Yeah, so of course it's a different author, but then, they motivated us towards thinking from an experimental perspective. And this is of course, just to elaborate on what we were just saying, that, the kind of paths which we would capture from that way of thinking would be these paths which go through the slit, without just go from source to detector through individual slits. These are what we would call the classically dominant paths, the ones which extremize the action, let's say. And then there would be paths of this kind and many such paths which would come up when we open up more than once, and so this is what we called classically subdominant, and in our paper we call it non-classical, but let's not get into the fact, it's not a quantum path. Non-classical means classically subdominant. We have defined it, so that is an usual question people ask, but now we can't take back the definition. So its paper is done, so I just keep telling you that this is what we mean, okay. So these are the subdominant ones. And of course, we have worked on, using such slit experiments towards testing Born rule earlier. This was the first such test which I participated in when I was not even here, right? So that was at IQC. But this is what we came up with, which is an experimentally friendly way of testing this contribution. Okay, so this is how we propose that we can use the same parameter, which is called the Sorkin parameter, which can be used now as a test for these subdominant, classically subdominant paths, okay. So this was the theory proposal, and of course Sam and Shupurna were involved in this, who of course we all know as colleagues from RRI and others, right. And this was a follow-up that we did, where we actually had an analytic handle on the problem. The first one was numerical, and here we actually came up with an analytic closed form expression for kappa, as we call it, which is the Sorkin parameter, okay. And there is an experiment which the Boyd group came up with. People in optics know Boyd. We all studied nonlinear optics by Boyd. And so the Boyd group came up with an experiment to apparently test our theory. Yes, you have a question, Shonji?
Yeah, so instead of closing one slit, is it possible to put a diode?
Diode?
Where the light cannot go from this side, but it can come from the other side. Yeah. So then your psi and psi b should include all, right? Like all these things, because
see, let me just, so it's a good question, because you see let me just tell you what these guys did. It's a, related idea, I would say. What they did is, they actually took a sheet, covered it in gold, okay, and sort of, marked these slits. And so the gold actually leads to what are called surface plasmons. So the surface plasmons, they led to an effective interaction between the slits, which led to an enhancement of the Sorkin parameter. So there are different kind of ways we can come up with to motivate, how we can handle this. But what we went on to do is exactly do what we proposed, which is a geometric contribution. This is important because this is a material enhanced contribution that the Boyd group ended up measuring. But we actually closed and opened, which is precisely the geometric formula that we found. So we matched with our closed form expression. But then there are different ways we can come up with.
Like Reggie was talking yesterday, this, what we call it, light diode for lights, right?
That
so that's
idea.
how I remember, like, so if instead of closing that, if you put a diode,
yeah.
so that will take
So if I
into
put a
account of this
diode,
rule,
no, I mean, only trouble that I have with this is that if I put a diode and if it is one way, then of course, what will happen is I will have both that and any other path.
Yes.
But then I want to separate out this Sorkin parameter,
but
separates it out.
That if I call it psi A, so that will take
Then it's
care
fine.
of only the going
Then
on the
psi
first.
A prime I would say in my mind plus psi B prime would solve the problem.
Yeah, exactly.
But what I want to do is show you that psi A prime is different from psi A. So I want to come up with a way where I can do a null experiment which only becomes non-zero from these contributions, which will happen in this way and not quite, so you see, yeah. So now this is what they did, and this now Sumati as a theorist, what do you think of this match? So these are my experimental data points, not mine, Robert Boyd, and this is the theory from our formula is the claim. So what do you think of the blue line and these blue dots? Would you call it the best match you have seen? New color, yeah. Okay. So somebody is answering my question on Ranjini's phone. But then, of course, I don't want to put Sumati on the spot. The point is that, the point is these are the data.
Very good. If you want me to say yes, in my opinion, it does look very good.
Yeah. So I want you to say that, of course, because I'm saying that, but I don't want to be the only person saying that. And so then, these are the data points which perfectly match with the dips, but there's nothing at the peak or the slope. This is not the experimental data point, only these guys, okay? So naturally, you can fit a parabola if I really wanted to do that. So this was the result from the Boyd group, which had some shortcomings, let's put it that way. And so this is our result, and Som is here. Thanks for coming, Som. So without him, the experiment wouldn't happen because we didn't know about antennas and things like that at that time. And so we went to Gauribidanur Observatory and did an experiment in an open field with an antenna as a source, an antenna as a detector, went to 6 gigahertz domain because that is the geometric effect we wanted. So kappa is 10 to the minus 2. Okay, and so these are the experimental data, and this is the theory band with errors and all. So we do have guys at the dip, peak and slope as it should be in most good fits. So this was a clean result. We could also use a baffle and take the effect off and on. So, we could kill the effect and bring it back and so on. So this is, our contribution, and I had some appreciation for it. Having said that, the latest thing we have done with the Sorkin parameter is measured it on a quantum computer. So, yeah.
So this was just a classical
No, it's Maxwell's equation.
That's what I'm saying. Just
that's
a
why I
Maxwell
said
equation,
it is
right?
a boundary value problem. So why not? So and in fact, it's a very good question. The Feynman paths are not restricted only to quantum. So they can be equally applied anywhere. So it's a boundary value problem, electromagnetic waves. We matched it very nicely with FDDT simulation and so on. Yeah. So indeed, we went on to do that. So the other end really. And we have now measured it on a quantum computer, and so that is nice because it's a different system from photons for a change. And so of course the idea is to use foundations of quantum mechanics and put precision on the quantumness of a quantum computer, so to speak. And so this is something we have done. I won't get into too much detail here, but this is another guy where we have done the error analysis and seen how much quantumness these quantum computers currently have. Answer is not very positive. So, we really have a lot more work to do to have high precision, noisy, intermediate scale devices is our current conclusion, but we will use more and more fundamental tests to keep testing these computers that we have access to. Shifting gear, this is on entanglement studies, and so this is Ashutosh who set up the first entangled photon source in our lab and arguably in India. And so this is an experiment which is on sudden death of entanglement, and it is revived by Soumyaranjan Behra, who is, very close to manipulating it. So what we are doing here is, so this is sudden death. This is something which is asymptotic. Again, a detail that I will skip for now, but having said that, what we are doing is coming up with local unitary operations so that we can make the sudden death happen later, earlier, or not at all. So which is what we call manipulation. The theory part, Ashutosh has talked about in many in-house talks and so on. The experiment is currently looking very good. So this is our sudden death problem. This is a series of work we have done on weak measurements. Again, a talk by itself, but then, using weak interactions followed by strong measurements, you can come up with things which you otherwise wouldn't. So you have a system, you are measuring it, but in between what is happening to the evolution is usually a mystery. But by using weak measurements, we can actually comment more on that. And we have done some interesting stuff related to that. Next 2-3 minutes, I will talk about our approach to quantum computing, okay? And so in quantum computing, we hear a lot about qubits and two-dimensional systems, superposition, so on and so forth. So what we are doing is, we are working with qubits, and of course we didn't come up with the word. Qubits is B replaced by D, where D is greater than 2, so higher than two-dimensional systems. So if you have 2 qubits, then you have 4 states accessible. So if you want to declare something which has 4 results, you will need 2 qubits. But if you have a Q-quad, which is a single system with 4 states, then you can have one system do the job for you. So essentially the idea is that by using a higher dimensional system, you can have access to a similar dimensionality to state space than by using a lower dimension. So smaller number of systems, which is nice because everybody has been after 2 to the 50 for a long time. Now we have reached that as a community. But that 50 number was important to reach that exponential space, right? 2 to the power 50. But if I make 2, 3, then 50 will drop. And so 3 to the power, it's actually 33 or things like that. So by using a smaller number, I can actually have that same dimensionality. And so this is something we are working on in different domains. And again, students can have a look at this if you want more info. So this is the series of work that we have done. Yeah.
Normally you'd imagine that the issue of decoherence comes in, right? So the larger the systems, So here, just by having more states, is there equal worry about decoherence?
So this is a very good question.
How does it grow?
So we have actually done them. So I was just looking at that. That article is not here, but I can share it with you. So we actually, tested decoherence models using qubits, and we find that it is quite robust. And in fact, in a work which is currently ongoing, Animesh is here, we have actually tested this for different entangled systems also, and we find that higher dimension actually gives you more robustness than lower. His PhD was on higher dimensional cloning, and so there is actually, it's a reverse actually. It comes out, and we can discuss more. The paper itself is missing from this list, but I'll share it with you, and we can have further discussions. Yeah.
So
It's
why not
something like that.
Yeah, so why not just use a quantum harmonic oscillator? You have infinite number of states, right?
That's a very good question. You are asking very good questions today, Sanjeev. So I just
ask, I think.
yeah. So no, not that you don't other days, but
Yeah.
So so this is maybe she will say more about it. But then having said that, infinite dimensional system. So one of the examples is orbital angular momentum of a photon. So it is in principle, and Komudi's PhD was on that. So you have an infinite dimension. Then what you have to, but of course, you can't really define operations for n equal, you have to have some finiteness in there to be able to define gates. So what they do, the community which works from top-down approach, they actually put in truncation, okay? And so then from infinite, they bring it down to some finite dimension. Yeah, so for your example, it will be up to n equal to 100, we somehow truncate. But then the problem is that if you take that approach, and that is done, you take that approach, and what happens is there's always going to be some, because it's an experiment we're talking about. So whatever you theoretically may be okay, but experimentally we'll always have some leakage from the modes which we think we have truncated. So you have done something experimentally to bring it down to 100, let's say, but then there is going to be some small leakage coming from this, and then as and Barry is going to talk about this on Friday actually, more about these topics. But then what happens is this then gives you a confusion about whether it is 100, and this 100 plus delta makes it not defined anymore. So then you do not know how to go about defining your gates and your protocols and so on. We are doing a bottom-up approach, which is the opposite of what I said. So if you have a single photon incident on a plate with 3 apertures, let's say, then it could be going through this, this or this, then these are the 3 possibilities for its spatial degree of freedom. I don't know which one a priori it is going through, so I form a superposition. This is what is called a spatial qubit, or in this case qubit, because it's 3. Okay, and so, but then what we did is we reversed the problem, and instead of actually putting these apertures in the path of a single photon, we are putting this in the path of the pump beam. If you remember the pump beam from a few slides ago, we are modulating the pump beam itself so that whatever comes out of the source already carries the structure through. And the daughter photons, as we call them, carry the mother photon characteristics beautifully, much better than humans. So it's almost perfect, and so this is the thing. So this is pump, this is single photon, okay? And in our case, this is pump, this is single photon. So you see, it carries it through really well, okay? And we went on to show that it has perfect 1, 1, 2, 2, 3, 3 correlation. We have a bipartite Q-trit system in the lab. So this was the first result, but then we have done a lot more. But then, Sanjeev, you should have questions on this, but maybe after the talk, we have, so no, because this guy being in the second row makes me happy. Yeah, so somebody's listening to me. So how do you measure entanglement in a higher dimensional system? Again, we answered this a little bit earlier, quantum state tomography, you can reconstruct the state, from there you can derive an entanglement measure. But that's d square again, it scales as d square. Oh, so these are two photons, Q-trit cross Q-trit, 3 cross 3 system. Yeah, of course. Yeah, otherwise entangled, yeah. But then we are going to make it 4 cross 4 and 5 cross 5 and so on and so forth. But then, so we have come up with an alternative way of measuring entanglement where we are using statistical correlation measures like mutual information, things that I'm sure, that's why I said you should have this question. I can't hear you anymore very well. Yeah. Normal, and it's also normal entanglement.
Density matrix, no? I mean, like you have a joint density matrix, and, but that's...
How, you have to measure the density matrix.
Yeah.
That is the problem. So in an experimental scenario as well, of course we are thinking experiments. So if you have a 3 cross 3 system, then actually it leads to an 81. So 9 cross 9 becomes, so d square. So then it, if you don't make any assumptions, it will actually involve 80 measurements because the trace row is 1. So it scales really badly as you go to higher and higher d. So what we have done, that's what I was just coming to. So instead of trying to do that, what we have done is we have found analytic relations between statistical correlation measures like mutual information, Pearson correlation coefficient. I'm looking at you because this is a statistical mechanics things which you must be doing all the time. And so we have related them to measures of entanglement like negativity, entanglement of formation. And so this is the theory work which does that, and in this we have shown it experimentally. By doing only one set of measurements, I am able to give you exact negativity. I mean, capital N, no negativity otherwise, but the exact amount of entanglement, which is not possible so far. So you have to do whole tomography, and you can do reduced density matrix, you can do many things, many different measures. But here we are measuring negativity just by doing statistical correlation measurements because of the relations we have found, which is pretty neat, and I'm not discussing more than that, but something we can. And so these are our next things, we're going to do lots of different types of protocols with collaborators like Barry and others in theory and so on. Last 5 minutes of my talk, I want to spend on something, so on something which I have a lot of backup, because tomorrow there is a talk by Kaumudi Bikash Goswami who is going to spend 40 minutes discussing this. So I'm going to do only 5, Kaumudi, pressure on you. So quantum communication. What is quantum about it is of course the key distribution. Dr. Sita did a very nice job in the inaugural session discussing something that she doesn't even do for a living, but then beautifully explained. So it is the most practical quantum technology because we actually have products which are available. But why are we still in business is of course the question, because it's not that these products are actually using protocols which have security analysis well proven. And so the kind of protocols we are working on, we don't have products out of them yet. So there is a lot to do as a researcher, so no worries there. Why you should worry, however, is of course, if you're doing any of these things, the students out there are also have access nowadays to credit cards and all that. So these are all examples of what I would call strategic communication. So anything that I want to send to Reggie, Subbu should not know. So how am I doing that? I'm sending something, encrypting it in a key. He has the key, he's decrypting it. But if he gets hold of the key, I have a problem. And currently how I'm handling this is using classical communication, which is called classical cryptography, which is based on the hardness of mathematical problems. So hardness of mathematical problems is the issue. Classical cryptography, RSA, is based on factorizing large numbers. And this is the hardness is only so good because Peter Shor came up with Shor's algorithm, which will change the hardness on a quantum computer. So the hardness is only today's hardness. It may not remain equally hard tomorrow. So computational resources grow very fast. Today's hard problem could be solved tomorrow using a brute force attack. New algorithms for classical computers also. Why just quantum? Quantum computers are anyway coming up, but even classical computers can run algorithms. And so my security should be independent of future advancements in computational power, algorithms. It should be future secure. And so this brings forth the need for a quantum solution, which is quantum cryptography, and the main part is key distribution. Having said that, this is a warning slide I always put, that we need around 4,000 qubits and 100 million gates to be able to break the kind of keys that will really bring about this threat. So some of you may say, why are you worrying about it now? Because we don't have this at the moment. But there is a lot of research happening. We will have it any day. It's not like it will happen. When I joined RRI, I was told, what is the point of quantum information? Ye sab to hoga nahi. Maybe after I retire something, but now it's not true. And so this also could happen in 4 or 5 years is the prediction. So you need to find the solution from now. You don't want the catastrophe to occur before you find a solution. So we are working on experiments in Bengaluru at RRI. So these are the various people contributing. Sujata, of course, has preceded me at RRI, but then has played a very major role in many of our developments. We are working on satellite-based QKD, which is our country's first project on it, integrated photonics-based QKD, chip-based QKD, QKD for the common man. You and I can put it in a phone one day. Quantum teleportation, we have students who are working on this, and device-independent random number generation came up in Barry Sanders' talk last week also. So these are all our areas. These are the past members who have contributed a lot towards this effort. This is the topic of tomorrow's talk. Quantum experiments using satellite technology use a satellite as a trusted node to establish entanglement-based QKD between 2 Indian ground stations using a satellite as a trusted node. Now, why is this experiment exceptional is the slide I wanted to really say a minute on. This is, of course, India's first project on satellite-based quantum communications. It started at a time when the field was not that popular, and its achievements have played a major role towards putting us, overall becoming so popular that many people are working on different areas. Why security in communications is important, you know by now. But it is actually something which needs to be operational across long distances. Otherwise, what is the point of Sanjeev and I communicating securely? We need to do this with a different country. And so satellite as a trusted node is a novel means of enabling this. So these are the 2 general ideas. The Chinese satellite, which demonstrated QKD, did downlink-based QKD, as they call it, where the photon source is in the satellite, 2 photons going through 2 ground stations, establishing a link. What we are working on is uplink-based QKD, and this has never been shown before globally. And why is it important? Because then it allows for my photon source to be with me at the ground station. If tomorrow Mandira comes up with a brighter source, I can replace it without having to bring the satellite down, which I will not be able to do. So I have a lot of flexibility with changing the source. I can put in quantum memory, tremendous scope I have for doing new and interesting things, as opposed to sending it away from me and then losing track of it for a few years. So this is the talk by Kaumudi. We have done a lot of achievements in this experiment so far. And of course, this is the big picture. This is what we are looking forward to, the entire world having a global quantum communication network. We have done in-lab QKD experiment, which has competitive key rate and error rate. And it is India's first reported end-to-end QKD experiment, which is published in an internationally peer-reviewed journal, which we care about a lot. This was the first experiment we did. This was, of course, proof of principle. We did the demonstration between 2 buildings. Atmosphere is very important. Satyaranjan spends his whole day analyzing atmospheric analysis for us and figuring out where should our ground stations be. Okay, and so this is the first step towards that. Kaumudi will tell you about this new way we have found to come up with a new feedback mechanism so that we can go towards long distances without worrying about active feedback. So that's in his talk tomorrow, and Barry in his talk will cover QKD Sim, which is a simulation software we have found which takes into account all kinds of imperfections. Okay, so these are snapshots, this is the overall picture and some appreciation from different quarters. And more importantly, DST, because they never notice what we do. So sometimes when they do, it is always heartening. And I would like to acknowledge all these people, the humans, as well as, the various, in different categories of humans, I would say. For a change, I want to acknowledge mankind. And so this is the whole list of people I would like to acknowledge. And of course, a little bit about Savita, because her calmness really helps us get through the day. I want to end with this letter because, after all this, I just want to make one last point that experiments don't work in a day. They don't work in 2 days, 3 days either. They take months, sometimes years. I think Sadiq knows this. So then he's smiling at this point. So it is indeed a long-term thing. So when you get a letter like this after you do an experiment, so this was a letter we got from the son of Max Born after we did the first experiment to test Born rule. And so this is, he says that he's very pleased with this work and, he was 5 when Max Born came up with Born rule in 1926. He wrote the letter in 2010, so he's not a very young person. He passed away 2-3 years ago. And so, he talks about how there was no experiment for 3/4 of a century and how he was very close to his dad and he was very glad that, we did this experiment. So first of all, it teaches us that, even somebody with a Born surname can be so humble. I have looked him up. He's an exceptional scientist. I mean, he was in his own field. And so, this is the letter I look at when, things don't work in the lab or when things happen outside which pull you down. And I go back, look at this letter, and I come back very pleased. So with that, thank you for your attention.
Thank you, Urbasi, for a very nice talk. It had a lot of glimpse of body of work you have been doing for the last 10 years.
Yeah.
Very nice talk.